Number 1 gives you a rate of flow. And so whenever you're given a rate, I like to think of it as this is already the derivative of the function. So when we start looking at amounts, we want to look at integrals. If we take a derivative of this function, it'll be the rate of change of that rate. So that's something to keep in mind as we go through this problem. So when we go to part A, we have these different values, and it asks for the integral from 60 to 135. So we're taking an integral of a rate function. So for the integral of the rate function, that will give us the amount. And then it wants a right Riemann sum, which means that we are going to choose the rightmost endpoint for each of these. So we're going to leave out that leftmost endpoint, and we're going to choose the right endpoint. So between 60 and 90, we're going to choose 90. Between 90 and 120, we're going to choose 120. Between 120 and 135, we're going to choose 135. And we're going to measure out the bases of each of those. Between 60 and 90, that's a distance of 30. Between 90 and 120, distance of 30. Between 120 and 135, distance of 15. So our interpretation is going to be an amount. That is the integral of the rate. So it's the amount in gallons, right? F was in gallons per second, gallons per second. So the integral of gallons per second should be in gallons. Pumped in between 60 and 135 seconds after the pumping began. So then here is the right Riemann sum. There's 3 subintervals, so there's 3 of the rectangles there. So 30 times the value at 90, plus 30 times the value at 120, plus 15 times the value at 135. Gives me 8.25 gallons for our units. It did ask for units, so make sure you put units. Part B said, must there exist a value of C such that f prime of C equals 0? If you're looking at a problem, you want to know when the derivative equals a certain amount. If you want to know if the derivative can equal a certain amount, that should ring bells for you that, hey, this is a mean value theorem question. So the first thing I'm going to say is that because f is differentiable, f has to be continuous. It gave us differentiable. So we need to say that the function's continuous and differentiable in order to use the mean value theorem. Then we're going to do our average rate of change, f of b minus f of a over b minus a, which in this case turns out to be 0, which is good news for us. That was the value we were looking for the derivative to be. So there's a value of 0. The derivative has to equal 0 at some point in there because of the mean value theorem. There's another theorem called Raleigh's theorem that you could have used since we started and ended at the same point, which is kind of a corollary of the mean value theorem. But I think it would be expected that most people would use the mean value theorem there. Part C now gives you a function for that rate of flow. So now we type that function into the calculator, and it asks for the average rate of flow. Well, rate of flow is that function, so it wants the average value of that function. Since it wants average value, that's going to be 1 over b minus a times the integral from a to b of the function. So it'll be 1 over 150 minus 0 times the integral from 0 to 150, which was 0.096 gallons per second, because it's the average value of g of t, so it should match the units of g of t. Then finally in part D with this function, find g prime of 140. This is where we need that interpretation of the derivative. G prime of 140, just type it into the calculator. And g prime, remember g is already the rate, so g prime will be the rate of the rate. So the rate is decreasing at a rate of 0.00491. Since g was in gallons per second, g prime should be in gallons per second, or gallons per second squared. make sure you should either say that it's changing at a rate of negative, or you should say it's decreasing at a rate of positive. If you say it's decreasing at a negative rate, then that actually means it's going up. So be careful with that when you phrase it like that. On to number 2. Number 2 gave you velocity, and we're working with velocity. Find when Stephen changes direction. So we're going to give a reason for our answer. I like to start with explanations first so that I know exactly what I'm looking for. We're defined from 0 to 90 because it says it's the first 90 seconds. So we change direction when velocity is 0 and changes sign. And we get exactly 56. And hopefully that makes sense if you look at the function, because this part, the e to the x function, that's never going to be 0. But this is going to be 0. This is going to be 0, and that's when I either have sine of 0, which is why 0 is there, but it's an endpoint, or when I have sine of pi, and sine of pi happens when t is 56. So that's why you didn't get a messy decimal and got an exact value out of there, which is not as usual for a calculator part. Part B. Find the acceleration at 60, show the setup, and indicate units of measure, and are we speeding up or slowing down? So first off, if we want to show the setup of acceleration, how does acceleration connect to velocity? This is what they're looking for you to say. Well, acceleration is the derivative of velocity. So I want v prime of 60, then put it in your calculator, and meters per second squared for acceleration. And then we're asked, are we speeding up or slowing down? Well, we have a negative acceleration, but that's not enough information. You also need velocity. And so even though there's a negative acceleration, the velocity says, hey, we're traveling to the left. And acceleration says, we're pushing you to the left. So it's traveling to the left and we're being pushed to the left. That means we are traveling in the same direction we are being pushed, which means we're going to speed up. Velocity and acceleration have the same sign, therefore, we are speeding up. Part C. Find the distance between their position at 20 and the position at 80. You might have thought of something that you're going to do in part D when you saw distance, but if we want the distance between the positions, then we just need to subtract their positions. So I need the position 80 minus the position at 20. And that's how I would find the distance between them. So I'm going to subtract those two positions. And to find s of 80 minus s of 20, well, by fundamental theorem of calculus, that is just the integral from 20 to 80 of velocity. Because you would exactly take the antiderivative, which would be position, plug in 80 minus plug in 20, and that's exactly what we're looking for there. So it would be the integral from 20 to 80 of velocity. Then when you go to part D, this is in meters, by the way, because we have position. Then in part D, find the total distance we swim over the interval. So that's our total distance traveled. That's our integral of the absolute value of velocity. That's your total distance traveled between 0 and 90. Integral from 0 to 90 of the absolute value of velocity. And that is your calculator section. Off to the non-calculator section. We start with milk. We've got a bottle of milk placed in a pan of hot water to be warmed. We have an increasing function that models the temperature. M is measured in degrees Celsius and T is number of minutes. And we're also told that the temperature, that M is below 40 for all values of T. So first off, we sketch the solution curve. The solution curve should look something like this. We're also given when T is 0, the temperature is 5. So when T is 0, M is 5. So that's going to come in handy in the next part of the question. But this is what the solution curve should look like in A. Then in B, it talks about using the line tangent to the graph. So we want the tangent line. So to get the tangent line, we're going to go, it's going to be y minus the y coordinate equals the slope times x minus the x coordinate. But to get the slope, we need the derivative. So here's the derivative. Plug in 5 for m. M is temperature. Remember, it's not time, it's temperature. So we're told that the temperature is 5. That means 5 goes in for m. So that gives us 35 over 4, which is the slope of my tangent line. So to approximate the tangent line, use the tangent line to approximate it to, let's plug in 2 for t and solve for m. We find that m is 45 over 2, or 22.5 degrees Celsius at that point. So once again, to recap, the slope of the tangent line is determined by the derivative. So we're plugging into the derivative and using that as the slope of my tangent line. And then plug in 2 for t for the approximation they're asking for. Down in part C, write the second derivative in terms of m. So they don't want you to leave it as dm dt. They want you to go back and put it in terms of m. So an m needs to be in this answer. Then use that to determine whether we are an underestimate or overestimate. And remember that underestimate or overestimate is determined by concave up and concave down. So first off, the second derivative, derivative of the 40 minus m, if we could distribute it out, we would find that it's going to be negative 1/4 dm dt. Right? We took a derivative of m, so we need a dm dt. Well, we know what dm dt was, so we're going to plug in dm dt here. Then after that, that's negative 1/4 times 1/4 is negative 1/16. And we were told earlier that m doesn't go above 40. So since m doesn't go above 40, this is going to stay negative the whole time because it's going to be a negative times a positive in here. That's going to give us a negative. So if dm dt, the second derivative is always negative, that means we're always concave down. And a concave down function, the tangent line is going to sit above a concave down function. And you can draw a picture to kind of verify this for yourself, which I did over there. That the tangent line will sit above that point. So we're overestimating m of 2. And then finally, part D. Part D asked for separation of variables. Use separation of variables to find an expression for the original function. So we're going to start by separating our variables. I'm leaving the 1/4 on the other side. This negative out in front right here, don't miss it. It's because of our chain rule. That would happen with the 40 minus m. Derivative of 40 minus m is negative 1. So I need the negative out in front to counteract that. I took away the absolute value bars because 40 minus m is never going to be negative because m is always below 40. Then rewrite it with e to the negative 1/4 t plus c. And then remember, I can rewrite that as e to the c times e to the negative 1/4 t. And e to a constant is a constant. So finally, subtract 40, divide by negative 1. Now that m is by itself, I'm going to plug in my point of 0 for t and 5 for m and solve for c, which gives me my final equation. Next question, number 4. Number 4 had a lot of moving parts to it because it asked about limits. It asked about maxes and mins. It asked about concave down. So there were a few different things going on here. So when I have a graph like this, if I know I'm looking at the original function at some point, then the first thing I do is I start to compute some areas. So that's what I did here. I've got a triangle with an area of 1. Moving from left to right, I have a triangle with an area of 1. I have a triangle of -1, triangle of -2, triangle of 2, and then I have this semicircle that's sitting there. Now, the semicircle is not what we're finding. We're finding the stuff outside of the semicircle. So that's why it's going to be 8 minus 2 pi here, because it's the area of that rectangle. Here, it didn't show up as well. It's the area of this rectangle taking away the actual semicircle, which leaves me with the actual area in green here, because I do want it, that I want. So rectangle minus the semicircle gives me that area of the 8 minus 2 pi. We're also told that f of 2 equals 1. So if I wanted to write the function, it's the integral from 2 to x, so that when I plug in 2, I control this integral being 0, and then plus 1, because I actually want f of 2 to be 1. So that's going to come in handy when we move down to part D and start talking about maxes and mins. But let's back up and talk about part A. Part A asks about relative maximum, relative minimum, or neither at x equals 6. Well, at 6, that's the bottom of the semicircle there. At 6, what's happening? Well, the derivative is 0, which is a great start. But remember that the derivative, in order for it to have a max or min, it needs to change sign. It either needs to change from positive to negative, or go from negative to positive. And here, to the left of 6, the derivative is positive. To the right of 6, the derivative is positive. Therefore, it does not change signs. So it is neither a maximum nor a minimum, because that derivative doesn't change sign. Part B. Where is f concave down? Remember, your explanation should be in terms of f prime. So f is concave down. You know that f is concave down when f double prime is negative. So let's connect that to f prime. If the second derivative is negative, that means the first derivative must have been decreasing in order for the second derivative, the derivative of that derivative, to wind up being negative. So I want to know when f prime is decreasing. So I always start with that explanation first. Connect the calculus idea so that you can look at the graph and you don't have to think about the calculus. So I've connected, I've thought about, okay, I'm looking for when f prime is decreasing. And so then I can go up to the graph and say, oh, that happens here and here. So from -2 to 0 and from 4 to 6. Those are when we're concave down. Part C, limit as x approaches 2 of the function. This is your L'Hopital's rule question. So I'm going to point out that the function is continuous and differentiable, because that's one of my conditions for L'Hopital's rule. Then I'm going to do limit of the top, limit of the bottom. I'm going to do them separately, and I'm looking for that indeterminate form where top and bottom are both 0. So the limit of the top, well, 6 times f of 2 minus 3 times 2. Well, f of 2, we're told up here is 1. So the top is 0. And the bottom, plug in 2, I get 0. So we wind up with that indeterminate form of 0 over 0. Therefore, we can apply L'Hopital's rule, which is derivative of the top over derivative of the bottom. So let's plug in 2. F prime of 2, well, here's f prime. So f prime of 2 is right here, it's 0. And then we're just plugging into everywhere else, and we get -3 on top, -1 on the bottom, which gives me a +3 in total. Then finally, over in part D, we want the absolute minimum. We want the absolute minimum. That means that we're going to check when f prime, if we want a minimum, when f prime to change from negative to positive, and then we're going to compare it with the endpoints. So here's where all those areas are going to come into play here. So first off, f has a minimum when f prime changes from negative to positive. I write that explanation down, then I look up at the graph. Where are we changing from negative to positive? Oh, it's at 2. So x equals 2 is our candidate for a minimum. Well, luckily, we already know what f of 2 is, so that's done for us. That's 1. So we just need to figure out the function at the endpoints, which I showed a little bit of the work here, but I've already done most of it. F of 8 is 1 plus 2 plus 8 minus 2 pi. So that's 1 where we start, plus 2, which is the triangle, plus 8 minus 2 pi, which is that semicircle thing, the outside the semicircle part. So that compiles up all the area between 2 and 8, plus the fact that we started at 1. Over here, at negative 2, I'm showing this work here, the function would go from 2 to negative 2, but that's the wrong order of the bounds, so we switch the order of the bounds and change the sign to be negative, which is why that area counts for positive 2, so we get 1 plus 2 is 3. Another way to think about it is that the 1 and the negative 1 are going to cancel out between negative 2 and 2. So these two areas are going to cancel each other out, which means we move down 2. Between negative 2 and 2, we move down 2, and we end up at 1. So if we started at a point, we move down 2, we end up at 1, we must have started at 3. Therefore, f of negative 2 is 3. That's another way you can think about it. But whichever way you think about it, we're looking for the absolute minimum, and the smallest one of those 3 choices is 1. So therefore, the absolute minimum is at 2, 1. It was indeed at the critical point that we found. On to number 5. Number 5 was just making use of your rules of derivatives and integrals. So I won't go super in detail here, but you can look at all my detailed work if you need to. H of x is f of g of x. Well, that's great news for us because to get the derivative of h of g of x, that's just a straightforward chain rule. So it'll be f prime of g of x times g prime of x. And it wants us to evaluate at 7. So we're going to plug in 7. G of 7 from the table, g of 7 is 0. So that gives us, we want f prime of 0. And then times g prime of 7, that's 3 halves times 8, which is 12. Then we have more fun with the chain rule on part B, and we add in a product rule. We have f of x squared times g of x, so that's a product rule. So first times derivative of the second, plus second times derivative of the first. Now, that derivative of f of x squared is 2f of x, but then chain rule times derivative of the inside part. Derivative of f of x is f prime of x. Plug in 4. And we're being asked whether the function is concave up or concave down. So since this was k prime, that's why we looked at k double prime and found that k double prime was negative. Therefore, k is concave down. Then on part C, m is 5x cubed plus the integral from 0 to x. So find m of 2. Well, m of 2, the integral of f prime is going to be back to the original function. That's fundamental theorem of calculus. So antiderivative of f prime is f. Plug in 2 minus plug in 0. and then 5 times 2 cubed. So it'll be 40 plus 7 minus 10. That's f of 2 minus f of 0. Gives us 37 as m of 2. And then finally, in part D, it wants m prime, because we want to know whether we're increasing or decreasing. Well, the derivative of this function, derivative of 5x cubed is 15x squared. And then the derivative of the integral should just be f prime, which gives us, plug in 2, well, it'll be 15 times 2 squared plus f prime of 2, and that is positive. And if the derivative is positive, that means that the function is increasing at x equals 2. Finally, we're looking at number 6. Number 6, this is my favorite type of question where it tells you what the answer is, and you just have to get there. You just have to show the work to get there. So anytime you take a derivative of y, write a dy dx, it's a product rule on the left side. And then derivative of 2 is 0. Derivative of y cubed is 3y squared. I took a derivative of y, I need a dy dx. Group the dy dx terms together, factor it out, divide, simplifying our way to get to the answer that they told us we should get. Part B, after that, it said, find when the tangent line is horizontal, and then part C asked us to find the tangent line is vertical. So I'm going to talk about these together. In part B, tangent line is horizontal. Well, that's asking about the derivative because it asks about the tangent line. Horizontal, I want to know when the derivative is 0 because slope of 0 is horizontal. Vertical line, the slope is undefined. So that would be when the derivative doesn't exist. So that's the calculus part, and now we turn to the algebra. dy dx is 0 when the top is 0, which is at y equals 0. But when I go back to the original function and say, okay, where is y 0? Well, y isn't 0 anywhere. It's not possible for y to be 0. So there's no such point that exists because there's nowhere where the y coordinate is 0. But we have better luck on the bottom. If we set the bottom equal to 0, now we're doing a little bit of system work here. If we set the bottom equal to 0, let's do some substitution. X equals y squared over 2. So let's plug y squared over 2 in for x in the original equation, which tells me, if we work through the algebra here, that the y coordinate should be 1. And from the substitution that we just did, that gives me the x coordinate of 1/2. So to recap that again, we set the bottom equal to 0 because we wanted to know when the derivative doesn't exist. Then that told us a function for x in terms of y. And so now I can do a substitution in for x in this function. And that gave me the point of 1/2 1. Finally, in part D, here's a particle. The horizontal position is increasing at this rate. What is the value of dy dt? Okay, here's the easiest way to do it. That dy dx equals dy dt over dx dt. This is actually another form of how you could write the chain rule. You'll see the chain rule written this way in some books in this notation. So I have dy dx. I could figure out what dy dx is at that point, which is -4/3. I'm told what dx dt is, therefore I can plug in and find dy dt. Right? Multiply by that 2/3, and that would give me -8/9. Now, the other way to do it is to start with the original function and treat it like your typical related rates problem. So this is an alternate solution. And anytime I take a derivative of y, I'm going to write dy dt. Anytime I take a derivative of x, I'm going to write dx dt. And then I'm going to group my dy dt together, kind of like I did in part A. And then I'm going to plug in all the things that I have found. I'm going to plug in 1/2. I'm going to plug in the -2. I'm going to plug in the 2/3 for dx dt, solve for dy dt, and we would get the same answer. So either with that related rates or with that fraction of dy dt over dx dt. Either way. That was probably the trickiest part of the whole thing. And those are your free responses. Thanks for watching.